right. Hello and welcome, everybody. So today we are here to continue the discussion on NSO's new concurrency model. So when we were preparing for developer days, we realized that we really want to give you an insight into these major changes that we are planning. And then we realized that we have a lot to say. So we divided the topic into two sessions. Christian and Tree were talking about the overview on Tuesday. And today we are going to focus on more, well, we are going to be more focused on the conflict detection, what does it mean, and how can you get the most throughput out of NSO. Right. I'm Viktória and Claes. I work with NSO core, and yeah.
I'm Claes. I typically work with the lower parts of conft and NSO, the transaction engine, XPath validation, etc. But I've been part in this project implementing the new concurrency model. First off, I just want to reiterate, we have been focusing on increasing throughput, not reducing latency. So a good example to think about throughput is this road here, where there's 3 lanes going forward. Even though that road, if you compare it to a single lane road, even if those lanes have a lower speed limit than a single lane road, as long as you have more than one car passing on that road at any given time, you will have more cars passing over the same time period. However, if you only have one car or less, there will be less cars passing. So to utilize what we're doing, you need to do more things in parallel, because otherwise you will have potentially a slightly slower road, but with multi-lanes. But if you aren't using the lanes, you don't gain anything. Another way of illustrating this is looking at an illustration of the progress trace messages, where we have 5.8 compared to 6.0. This is the same service. We start 3 transactions and instantiate services on them. On 5.8, you can see that there's only one transaction that is allowed to run services at once. And then it does the validation, and then it does what we call the critical section. Well, it's all of this is the critical section, is 5.8, but it's named critical section because that's what we kept in the critical section in 6.0. And when that's done, the next transaction gets to execute. So there's a long gray waiting time there. When that's finished, the third one gets to execute. In 6.0, the services are executing in parallel. The validation is executing in parallel. And then we still have this critical section where we need to update the data store, we need to update the devices, etc. But you can see here that we are actually finished with all 3 transactions before the second transaction has finished in 5.8. So there's a big gain here. These are, by the way, old slides. So if I miss things, don't shoot me. So for us to achieve this, we have gone from a very pessimistic approach, where we had this very long critical section, to an optimistic approach. What that means for us is that we are doing more work outside of the critical section, and in order for us to do that, we need to do more checks. We have moved out the rollback file creation, which can be quite time-consuming, the service invocation, which includes your code, so it's impossible to know how long that will take, and the Yang validation. And now that runs outside of the lock, that allows us to run them in parallel. Yes, we have done this to trying to accommodate for the increased adoption of NSO and increases in network sizes, so you won't run into bottlenecks or performance issues, which you have already probably, but we will allow you to grow with us.
Right, but if you look at the progress trace where Claes illustrated with 3 transactions, what's the major difference between 5.8 and 6.0? What you should realize is that those are independent transactions. So, and life is not that simple, basically. So let's discuss how can we do more things in parallel, but still keep the same transactional guarantees. All right, so we do much more things in parallel. We create rollback files, we execute services, we perform Yang validation. All this goes in parallel. Now with parallelism, we still want to ensure the same transactional properties. So what we need to do is that we need to protect the decisions the transaction make. We do that by focusing on the reads a transaction make. Basically, you make decisions based on what you read. So reads become much more important. First, you would think that the only reads performed are through an open transaction handler, right? Before applying the transaction. But that's not really true. So when you apply a transaction, NSO starts reading a lot. NSO is going to read during rollback creation, during service invocation, during Yang validation. All these reads, all these decisions needs to be protected. So for that purpose, we collect the read set of the transactions. We collect the reads occurred at all phases. And then when we are about to accept a transaction, we are going to check if the decisions the transaction made are still valid. So in other words, we are going to perform a read-write conflict detection. What we are going to look at is that we are going to take the read set of the transaction that we are about to accept, and that is the one that we are going to compare with the write set of the transactions that have committed since our transaction has started. All right? What we are looking at if the decisions the transaction made that we are about to accept are still valid, or have they been invalidated by the rights of another transaction? If so, then we have found the read-write conflict. In that case, we cannot accept the transaction because we want to maintain the same transactional properties. All right, so if you look at the slide, you are going to, this is a Python code snippet, right? And what you see here is that, all right, so at line 4, line 1, we start a read-write transaction towards running. Then at line 4, we are going to read from the database. We are going to read the value of the counter. And then at line 5, we are going to increase the value of the counter, write it back to the database. Line 6, we apply. So after running this code snippet, the value of the counter will be increased by 1. Happy days. Now, assume that you have 2 threads running at the same time. So let's explore the scheduling. Now, of course, there is the sequential scheduling, where you have the first transaction running. After that is applied, the value of the counter will be increased by 1. And then comes the second that is going to further increase the counter. So at the end, the value of the counter will be increased by 2, right? Cool. Okay. Now, more parallel scenario scheduling is that the 2 threads are executed at the same time. Okay. Now, in that case, we have 2 transactions running in 2 separate Python threads. Both of them are executing line 4, which is reading from the database. Both of them are going to read the original value of the counter, right? Now, both of them are going to increment that value by 1. Cool. First one to commit goes through. No conflicts there. But then what will happen with the second one? So the second one is not going to be accepted. Why? So in the second transaction's read set, we are going to have an invalid read. We are going to have a read that shows that we read the value of the counter as its original state. Now, that value has been changed by the first transaction that we accepted. Correct? So the decision the second transaction made is invalidated by the first one. We cannot accept the second. So this is an example of the read-write conflict. So do you say that we have the...
No, we have reload slides.
Yeah, okay, good. So, okay, in that case, bear with us, but please assume, let's change a bit this Python code snippet, okay? So let's say that we remove line 4. Okay, we do not read from the database. I repeat, we do not read from the database. Instead, this value that we are going to set for the counter is going to be some magical number, I don't know, thread ID, timestamp now. You choose it. The point is, the value is totally independent of the content of the database. Cool? Now, both transactions does it. They are running in parallel. Guess what? Both are going to be accepted. Why? Both of their read set are empty. Cool. So then they cannot invalidate each other's decision. And the value of the counter after running both transactions is going to be the value the transaction wrote that was last to commit. All right? So this is a last write win rule, one could say. Okay. So now I guess this is enough about conflict. So let's talk about what happens if a conflict occurs. So as we talked about it, there are a lot of reads, right? Doing reads with an open transaction handler, and then while applying the transaction, NSO does a lot of reads as well. Rollback creation, service invocation, Yang validation. Cool. So when a conflict occurs, NSO is going to inspect the conflict. It's going to check at what stage did the conflict occur. Reading via open transaction handler, rollback, service, or Yang validation. Now, if it happened while you were reading, NSO cannot help. So in that case, like the counter example, if you were running it as an action, that transaction is going to be aborted. But if it happened while we were applying the transaction, NSO can help. So it's going to select the first phase, the first conflict that occurred, all right? And then it's gonna retry the transaction from that point. We are going to rerun everything. So this means that your service code, your Yang validation points, may be executed more than once by one transaction. That's a pretty important thing to remember, right? All right. Now, service conflicts are important. So let's talk a bit more about service conflicts.
It's
yes, back.
It's back still.
Yeah, cool.
Yeah.
All right. So we do consider that service execution can take time. So we try to be helpful to aid throughput. So when a service conflict occurred, a conflict that happened during service invocation occurred, NSO is going to do further inspections. So it's going to collect the services that have been invoked in the transaction that conflicted, and then it looks at the transaction that was conflicting with us and checks if there are services there as well. If there are, then we found a service conflict, services that invalidate each other's decisions. So that doesn't sound right, to run them in parallel. So in that case, NSO is going to register a service conflict. So it's a special type of conflict. We call it service conflict. And then whenever a new transaction comes in which have services, then we are going to look into service conflicts. And if we find that there are running transactions that would invalidate the decisions of the services that we are about to run in the new transaction that is coming in, then we will not allow that to happen. So in that case, we are going to serialize them. So this is not a permanent decision, so to say. NSO is going to test it, and it's going to learn over time what are the services that really conflict, and it's going to serialize only them. But so NSO helps a lot and resolves most of your conflicts by retrying, rerunning the transaction from point. But there are conflicts where we cannot help, all right? Like the counter example. So because of that, we provide new retry abstractions. These are APIs in Java, Python that you can use. So you could review your actions, nano-service side effects, and make sure that you use these new retry mechanisms and abstractions that we provide, because that way you can be sure that the change you want to persist is going to be persisted, it's going to go through, it's going to reach the network. And as well, it can be a good idea to prepare your OSS, BSS layer for retries. Yeah.
So, giving these changes, I guess you want to get the most out of them. So there's a few things to consider to actually make use of these things. As I mentioned before, you actually need to do things in parallel to start with, because otherwise you won't gain anything. Secondly, I'm going to go through, or we are going to go through a few points you need to think about. First off is to ensure that your code supports parallel execution. Secondly, we need to try to reduce the amounts of conflicts in our system and in your services. Thirdly, we need to try to avoid service restarts because it takes time. And last, we're going to talk about how to make NSO able to run as fast as it can, so we are actually working with it and not against it. Okay, first off, how many of you guys develop in Python? Raise a hand. And Java? Examples are in Python, it's good, but I just wanted to know. So first off, standard thread safety practices apply. If you have some sort of shared data, some sort of API resource in your service code, those need to be protected, typically with a lock. Second, if you have shared data, that has changed how that works with 5 or in 6.0. You have the possibility of using that in 5.8. I'm missing the slide that I'm going to talk about, but I'll go into that a bit more. Shared data same applies. You need to ensure that you update it safely. One thing when noticed when we have tried this out, we try to run this with real actual production code as much as possible to see that it actually works and is backwards compatible to the extent it can be. But one thing we have noticed is that there's Python code where you assign values in the service create callbacks to yourself, and then you go on and execute and do your work with those values. However, that doesn't work anymore, because consider having 2 services being created at the same time. Service 1 gets to execute, computes some values, assigns them to self, goes on, tries to use those values. And after a while, service instance 2 goes computes those values, other values, sets them to self. And then service 1 will end up in a very interesting state. It's hard to tell what's going to happen, but it's not going to work as expected. In NSO 5.8, there's a change that makes those assignments log warnings in your code. So you can prepare to use 6.0 by going to 5.8 and run your code, and you should get warnings in your logs stating that you're assigning values to self in your callbacks. Another thing that was introduced in 5.8 due to this project is the call point model. You can set in the package metadata. Previously, it's been threading, so every invocation of a service is executing a separate thread. But in 5.8, you could change it to use multiprocessing, which means that every call point in a Python package gets to execute in its own OS process. That was made to avoid any contention on the control socket, the socket that is open between NSO and the Python code, which where commands are served, and then there's a separate worker socket that replies, but there can be contention on the control socket. In addition, we have the Python global interpreter lock. We don't want any condition on that either, contention. So you can go to multiprocessing. You can do that in 5.8 to see that it works. Another good thing to prepare for, because it's default set to multiprocessing in 6.0. So if you would have a Python package with multiple components sharing some state, that won't work anymore unless you switch it back into the threading mode, because they're running in separate OS processes. Second, we need to try to avoid creating conflicts. And as Viktória mentioned when talking about conflicts, we now have read-write conflicts. In 5.0 and prior, we have write-write conflicts. But in 6.0, we have read-write conflicts. So now what you read is more important than it was before. It actually bears some meaning. So if you do decisions in your code, you now need to protect them with reads. Previously, you could have a long-running transaction open towards running and just read from that, and that was safe because when your service executed, no other services could execute and change what you read. That's no longer true, so you need to read through the transaction you're writing towards, because otherwise you don't get any protection of the data you read. In addition, you should never read something that you do not need. Like if you should never scan a list for something if you can pre-calculate or know which element you need to read, because that causes more reads to happen, increases the risk of conflicts and retries, and you won't get the same improvements in performance. And now we're lacking even more slides. So I was about to present a Yang model to talk about I just going to sure. Yeah. To talk about other types of conflicts. So, as Viktória mentioned, we have more types, or there's more reads than the ones you do when you apply a transaction. Yang validation is can be very read intensive. And so your Yang models become even more important as a factor to improve the performance. Another thing one thing you need to think about in your Yang models, apart from the validations, are lists. Why, you may ask? It's because as we use the read data as input to know whether or not your transaction is still valid, do the same with lists, but we don't have the intent of your read. So if you start iterating a list, you might be searching for something. Doesn't really matter. We don't know why you read it. So you read the full list. If you would ever add or remove from that list, that would be treated as a conflict because you have read the list. And we don't know if you base the decision on it or not. So we need to assume you do. An example of this would be to have a leaf in your database representing a concatenation of the key values in a list. If you would have the ABC keys in the list, you would compute the value ABC in the leaf. However, if somebody else would go about adding or removing from that list while you were computing the value, you would get a discrepancy between the computed value and the list elements. So that's why we need to treat any addition or removal from a list as a conflict. Secondly, we have schema constraints like when, must, etc. I don't have the Yang model here, apparently, but let's consider having a leaf that, an integral leaf, and then you have a list with a leaf in it that has a when expression. That when expression is dependent on the leaf outside of the list. So let's say you have 10,000 list elements. Doesn't really matter, you can have 10. But whenever you change the dependent leaf, NSO needs to scan the list and re-evaluate the when expressions so that all those leaves that might no longer exist because of the when expression going false gets removed. So that would cause a full list scan and increases the risk of conflicts. If you would have some piece of code simultaneously modifying that list, you would get a conflict. So lists, super important, and that applies to like all your schema constraints, when, must, unique. They do cause a lot of reads, and especially if you put them in lists, and or lists and lists, it's even worse. So that needs to be thought of. Do you have anything I should add while we don't have the slides?
I mean, the same holds for must expressions, right?
Yeah.
That we may perform a lot of scans of lists. So yeah, and here we should mention as well unique. That's as well a tricky one.
Yeah.
Right. So if we want to maximize throughput, then it means that we want to run services in parallel. Meaning that having service conflicts is not really a good thing, right? So if you have service conflicts, you are working against maximized throughput. So let's revisit this a bit more. Okay, so service conflict happens between services where the decision of one service is invalidated by the changes done by another service. Well, this can be two sets of services, but just let's go with two services for now. Now, decision made, they are reads, okay? Changes done, they are writes. So basically, the reads of one service is invalidated by the writes of another service. It can be just partially, right? I mean, just one decision being invalidated, that's already a biggie. That's already a service conflict. So when a service generates input for another service, because we could look at it like that way as well, those services are dependent services. And if you want to get maximized throughput, you want to avoid having dependent services. If you want to maximize throughput, what you want is to have services where the input of a service is independent of the output of another service. In that case, there will be no service conflicts. Everything can run in parallel, aiding max throughput. If you still need to generate input for another service, then use stack services. Like stack services are the design pattern where we have a top service that generates input for the bottom service. Since both the top and the bottom service is going to run in the same transaction, they will not conflict, and yeah, they will be happy, and you will be happy because you're getting max throughput. Another thing to mention here is whenever you have a conflict, and I think we touched already upon that, we are going to retry a transaction from a given point. So your service code can run multiple times. So having side effects is not cool. So if you have these old-style reactive fast map services, perhaps you want to convert them to nano services, because in nano services we separate side effect free code from code with side effect, and then you will be safe. Here is another thought. So if you do not have service conflicts, it means that multiple service instances of the same service point can run in parallel. This means that if the create code that you implemented for that service point is not thread safe, then actually you want to avoid that. In that case, you actually want to have a service conflict, so to say, because you want to serialize them, right? Correctness comes before throughput, so that's what you want to do. Now, NSO allows you to do that, so you can register all non-thread safe service points as singleton services, and then we will ensure that no two service instances of that service point will run in parallel.
Sorry. Now we can actually go back and revisit the Yang model example if you want to. It's the same slide now, so it's kind of useless, but we can do it like this.
Okay. So now will you show your examples?
I can show them now,
okay,
if you want to, or if it was perfectly clear, we can just move forward. Anybody wants me to do the examples again? Raise your hand.
We have time.
It's before lunch, so I know if you might not want to. Me too. Yeah. So where was I? Yeah. First off, we have the Python example. So in the Python package metadata, you have this new option called call point model. It's available in 5.8. I suggest you to try it out, because then you will be more prepared for 6.0. But it looks like that. It's easy to switch. Yes, so this was the Yang model I was talking about earlier, where we have the leaf L that the leaf O in the W list is dependent upon. You can just look at and read the model for a few seconds before I switch slide. So this just to illustrate the amount of reads that happens is on the right side here, your left, your right, my right, the right side, the correct side. Interesting enough, you see what happens when the L leaf was changed from 2 to 0. Basically deleting all the O leaves inside the W list. So it'll cause a lot of reads to happen, and it's also in a list. So it's prone to cause conflicts if you have things mutated in the same list at the same time. These are things that needs to be considered. Of course, they cost performance before, but you didn't have to worry about the conflicts and the performance degradation that come with them. So yeah, it's really important to think about that. Yeah.
Now I'm back again. All right. So have you ever heard about Amdahl law? So Amdahl law states that a parallel system is limited by the length of the non-parallelizable component. So you can try to achieve whatever concurrency you try to achieve. You are going to have a cap, basically, and that cap is caused by the non-parallelizable part. In case of NSO, that is the critical section. We have already moved out from the critical section, rollback creation, service invocation, and Yang validation. But there are still some parts left there, right? And if you have CDB subscribers, then they are going to run inside of the critical section. This means that the runtime of your CDB subscriber is going to extend the total length of the critical section. If you want to get maximal throughput, you should migrate from subscribers to kickers. And then when you use kickers, make sure you write nice ones, okay? So basically, try to avoid long and complex XPath expressions for the monitor expression or the trigger expression, because that will at the end take time to evaluate, right? And then this is all adding to the critical section that we have left. So you want to minimize that. And then there is another thing, which is a very important thing, is that if you disable commit queue, because I'm going to assume that all of you enable commit queue. So the moment you disable commit queue, propagating the changes towards the network, contacting the devices, loading the configuration on the devices, waiting for the device to acknowledge and persist the change and come back to you. I mean, it's even takes long to explain. This is all part of the critical section. So in that case, the length of your critical section is going to grow big times, and we have slow devices as well, right? So please enable commit queue, and let's remove persisting changes to the network from the critical section. Right, all good things end, and considering that it's soon lunch, maybe you are happy. So it's time for us to wrap it up. We are really happy to see that a lot of our customers are very successful. You have a growing network, and we want to keep being part of your success. So that's why we created this project a while ago. Our goal was to increase the throughput capacities of NSO. We want to do more things at the same time. We want to be more parallel. We want to perform more user commits at any given time. For that purpose, we created major changes. We introduced major changes in NSO. We went from pessimism to optimism. We do much more checking because we still want to ensure that we are transactionally correct. But of course, more checking will come at a cost. So today we talked about what are our new safeguards, the read-write conflicts. We talked about how they happen, when do they happen, and what happens if they happen, if you see. And we also gave you tips and tricks of how to get the maximum throughput out of your NSO installation. NSO 6.0 is coming this year. We are on it. And well, start planning, consuming it, start preparing, and remember that if you want max throughput, you want to minimize conflicts. You want to ensure that all your components are thread safe and they can run in parallel with each other. You want to minimize or avoid service conflicts, and you want to allow NSO to run as fast as possible. Right, and when you are in this journey of upgrading to 6.0, while you are at it, after you are at it, please talk to us. We would love to hear your story. We would love to hear your feedback. And with that, I think we are really happy that you attended this session, and we are happy to take questions now or later. Oh, lot of questions. Excellent.
Yes, about the thread safety, the log alerts that appear there, do they take into consideration if you use things like thread local storage or like an adapter pattern, so it's not actually on the service object, or do they just react to your code as assignment to self?
They just react to your code assignment to self, and they are only for Python at this moment. But yeah, they only react to assignment to self. There's room for improvement.
Can we disable them if we've actually thought about thread safety?
No, you can't. Actually, you can't. That's another thing that probably should be improved before the release then.
Hello. So I see there's a lot of deep changes. If we decide to migrate to 6.0 and we are, let's say, I guess it requires a lot of preparation as far as I can see because of this change from pessimism to optimism, which I like, I would say. But is there like a way to disable some of these new features if we're at 6.0, or would we have to like, just hit the ground running immediately to the new features?
Shall we fight about it?
Yeah.
There's some things you can disable, and there's some things you can make it look like an older system, but not everything. Let's say you can go to, in the Python package, you go for the threading approach. You can annotate all your services so that they have pre-existing conflicts, making them run in sequence. And what else can you do?
I mean, that kind of brings you back.
Kind of, but it's still not, then you still can do other things in, like if you have a lot of non-service interaction with your system, those transactions will run freely anyway. So those won't be, there's no way of limiting those.
And these features are, I guess, for Python mostly, but are there plans to implement them for Java as well, or is this something for the future?
No. I mean, all these major changes apply to Python, Java, template, everything. But I need to highlight something. So maybe we did our job too well and we scared you, but this was not our intention. We wanted to give you like ideas of how to get max throughput, and at the same time I need to highlight that we've been working with real use cases, and it is a very, very smooth. Well, this was always one of our project goals, that we want to have a very smooth upgrade experience. So we've been taking real life use cases installments that work with 5.x, and then just taking them, putting it into our engineering build of 6.0 and running them. All right, and I don't think we had to do a lot of changes there. Like, sure, if your service code uses self to share data between call points, that's like, I mean, premod create and then create. That's meh. But for that, you have the opaque that you can pass around the service opaque. And
but just to be clear, all of these would be supported in Java, so if we decide to go that route, it would be okay, or is there kind of a recommendation to go the Python way?
No.
No.
Okay, that's what I wanted to make sure. Thank you.
Yeah.
Like the multi-threading thing for Python is due to the fact that Python doesn't scale as well as Java does with threads. So there's we do compare service execution time. We have compared Python, Java, and templates, like doing just to see the overhead of the different types of services, not doing much work in them, and they perform basically the same. So it depends on in general, you're safe with what the rest of the things in the system that makes it slower, like the network, we are able to push enough. But it depends, of course, we can't predict all your service code. If it's very complex, yeah, that's another story.
Of course. Thank you very much.
I have a question on what I can put in the service callback. So, do you see me? Or
Yeah. No, there you are. Yeah,
okay, yeah. So imagine I have a service that does some reads from an external system, maybe something like a HTTP GET request from somewhere. And right now I have an NO service because that may take a while and I don't want to block, I don't want to be in the critical section for too long. But now that the create callback is being moved out of the critical section, can I do the GET inside the create callback, or is that a bad idea?
No, I mean, you want your service create callback to be idempotent. So if I run your service create callback having the same database multiple times, then I want to get back the same result. So, I mean, you can do it, but I think it would be nice.
Get, so hopefully that means it's actually like get.
Oh, okay, and then that stays the same. Yeah, sure.
Yeah, no, you mentioned there should be no side effects, so
yeah,
if I'm relying on the external system to give me whatever data, it's okay.
Then it should be fine, but the longer your service executes, and depending on how much you write, the higher the risk of a conflict occurring because other things complete during the same time period. So that's also a factor to take in. It depends on how independent your service is.
Yeah, and as well, if there are services that conflicts with the service that does this GET requests in the service create, then those services are being blocked to start run create while you are waiting for this HTTP server. In contrary, if you would do the gets inside nano-service side effects, then you would not block other services that would conflict with your service to run.
Yeah, for sure. And also there's the option of multiple GET requests and more load on the server because of that, but yeah. Okay, thanks.
Hello. Yeah. So if I understand correctly, in order to become optimistic, there is a little bit of work required. Might be, right? But also, if I want to stay pessimistic, it's not like just ncs.conf pessimism true.
No, well, we were actually discussing that early on. I was the yay-sayer. We have a naysayer there.
Hello.
but due to complexity reasons, due to be able to actually provide a stable platform, we did not go that route because this impacts a lot of the parts of the system. So that's why it's not an option anymore.
Oh, so damned if I do or damned if I don't or something like that.
Yeah.
Thank you.
So I'm not 100% sure that was already answered, but if a customer wants to migrate to 6.0, not only to grab the benefits from this parallelism, any other thing, it still needs to do this validation before it upgrades, or is there a way to enable or disable the parallelism? No. Yeah.
Nope.
Okay. Thank you.
I mean, there is this, you have the chance to do incremental upgrades, at least from point of view of services. Because if you just want to start it on and then incrementally get more throughput and enable more features, then how you could start the upgrade is that you register all services conflicting with all other services. And then you can get to 6.0, and then one by one, you can review your service packages, see if they are threat safe, and then remove those, remove those constraints that you put in. So you have that option, but you know, if you try it out in a test bed or something, that's good.
Hi. So when you're scanning for conflicts, you are taking into account when and must expressions.
Sorry, go on.
So do you also do that for Python validation hooks?
Everything that happens from the point the transaction starts, if it's a read-write transaction towards running, we collect all the reads that transaction does. There are exceptions to that. If you're using the CLI or the web UI, those are interactive sessions, so they do read a lot. So those are treated differently. There we only do partial collection to provide a better user experience, because you typically show a lot of stuff and you don't really care. But for the other transactions, we collect all the reads. So it doesn't really matter where they're happening. They're happening through the lifespan of the transaction. They will be read, and those will be matched towards the transactions that has written since you started or committed.
Okay, good. All right, thanks.
Is there or will there be an online resource describing your changes and maybe best recommendations and changes, recommendations and things you should and shouldn't do prior to your release, or do we have to wait for the release notes?
Well, for sure it will be part of the release. So we will make sure that we update the documentation. We include best practices guide.
But as you mentioned, it's probably a good idea to be as quick about it as possible. If you can do it up front so that you can start preparing, it's a good thing. But that's not really our table.
I hope somebody else listens. Is this year the best bet on a release date?
Yes, this year we plan to release.
Okay, so I think with that, we're prepared for lunch. If you have more questions, just approach the speakers as always.
Yeah.
Yep.
So thank you.
Thank you.